Assalamualaikum, my name is Sabrina. I want to talk about our aircraft engine bracket. Why we choose magnesium alloy as our materials? It is because magnesium consists of low density, which is 1.7 grams cm cube. It also lighter structure metal that can make a design to weight reduction. Magnesium alloy also fatigue resistant, which is engine bracket are subjected to cyclic loading, and alloy withstand these repeated stresses over the aircraft lifespan. And not forgetting, why we choose this design because of the rectangular base plate that act as support for the bracket, and the fixed support was at the bottom surface of the base plate. The four holes also designed for the fasteners and screw plates, while for the pocket was designed for reduce the weight that have been applied. Next, for upright and flange was located at left and height was 45 mm. The hole was used as a load and applied from the bottom to the top using 16,500 Newton. From this table result, we can see the value of the present design was achieved a good value, which is for the mass we got 0.57878 kg, that's below from 0.8 kg, and for the FOS was higher than original design, which means it's good. The value is 1.876, which greater than 1, and for the deflection is 0.16475 mm, which not more than 0.2 mm. And lastly, stress we can 102.88 MPa. The most striking difference is in the mass. The present design utilizing magnesium alloy achieved a remarkable reduction in mass from 2.05 kg to 0.5787 kg. This represents a significant weight saving for the aircraft, which is a critical factor in aerospace engineering, as it directly impacts fuel efficiency and payload capacity. The percentage difference of 27.65 is represent the ratio of the present mass to the original mass. The primary reason for this mass reduction is the lower density of the magnesium compared to titanium alloys. Okay, based on the pictures given, the stress value likely equivalent 1 meter stress present design a stress of 102.88 MPa is reported. The value represents the maximum 1 meter stress calculated with the components under the applied loading condition. The 102.88 MPa represents the highest stress concentration point within the optimal magnesium bracket when subjected to specific loads. Since the stress is significantly lower than the material implied yield strength, it indicates that the present design is operating well within the elastic range of the magnesium alloy. The present design with its 102.88 stress FOS is clearly better optimized to manage stress relative to the material properties. Deflection refers to displacements of the bracket under load. The original design deflection of 0.3 mm exceeds the acceptable limit of 0.3 below mm. Excessive deflection can lead to various issues, including interference with other components, fatigue failure, or reduced operational efficiency, while present designs deflection of 0.1647 mm that represent a significant improvement. It is well within the acceptable limit and is considered lower than the original design deflection. This indicates that despite of being lighter, the magnesium alloy design is stiffer and more resistant to deformation under the applied load. The 52.93 differences represent the percentage reduction in deflection from the original to present design. The present design significantly reduced deflection, leading to more stable and reliable component. The fact that magnesium has a lower Young modulus than a titanium alloy typically suggests higher deflection for the same geometry and load. The factor of safety is a critical measure of a design robustness against failure. The original design FOS of 1.05 is concerning because it falls below the specific acceptable range of 1.02 to 3. This indicates that the original titanium alloy bracket was designed very close to its yield strength and had a very low safety margin, making it vulnerable to accepted loads for imperfectionism, while the present design FOS was 1.87 that significantly improved upon this. It not only surpasses the original design FOS but also falls comfortably within the design range 1.2 until 3. This is mean the magnesium alloy bracket has a much higher margin of safety against yielding or ultimate failure under expected operating condition. The 56.33 difference likely indicates the percentage increase in FOS from the original to present design. However, the absolute improvement in FOS from 1.05 to 1.87C is a major advantage for the present design, indicating that a much safer and more reliable component.
Okay, for the next analysis is thermal stress analysis. So if you can see from the result, the stress is 170.24 megapascal. So the location of the maximum stress is located at the edge of corner of bottom surface, and the range is still within the safe limit for most high temperature materials. This will result the design will not crack and break easily. So for the next is total deformation. If we can see, the deflection is reduced from 0.43 millimeter to 0.18176 millimeter, and the location of the total deformation is at top left corner of upper right arm, and this design more rigid, and it has low chance to deform or the design to break. Uh, this will helps the bracket to maintain the shape and function under condition. Okay, so the last one is factor of safety or FOS. If we can see, the FOS increase from the original design to present design, and which is the value is 1.05 to 1.1337, and the location is located at the edge corner of bottom surface. This will result the low chance the new design to failure. It is because the higher factor of safety means the bracket can hold more load safely, so that it can be used in aerospace or bracket application. So based on table 4.5, which is results value of the present bracket design. So if it clearly be seen that the original design and present design have a very different value for mass. Okay, the original mass is 2.05 kilogram, and it reduced to 0.57878 kilogram. And if we can see that the higher value of deflection is at deflection 5, and the value is 278 and 25 millimeter, while the lower value located at deflection 6, and the value is 140.11 millimeter. So next is based on table 4.6, which is table of frequency analysis. In the module, it be stated that engine excitation frequency is 275.8 Hz, and the table 4.6 show the natural frequency from total deformation 1 to total deformation 6, and the range is within 6050.8 Hz to 121,832.0 Hz, and all the values recorded are higher than 275.8 Hz, which means this bracket will not experience any resonance, and also this bracket is safe to operate at high speed and can handle vibrations without failure. Okay, so the next slide, we are moving to each of the color contour plot of the deformation 1 until deformation 6. Okay, so in this slide, it has a two mode of deformation, which is mode 1 and mode 2. For mode 1, the higher value is 171 and 77 millimeter, while the mode 2 is 215.19 millimeter. So the location of the maximum value can be seen in the image above. Okay, so there are a few suggestions and recommendations that can be made to improve the new bracket design, which is we are selected four main point, which is material selections, factor of safety or FOS, area, and fatigue analysis. So the next slide will be the explanation for each of the properties. Okay, the first one is material selection. Material selections mean that the useful of material with high thermal resistance and greater yield strength. For example, is titanium alloy and nickel based alloy. Why we choose these two material? It is because both material can extend and very suitable for high temperature application. So the next one is factor of safety or FOS. So if you can see from the previous table, the current FOS is 1.1337. It actually still and close to failure. So the aiming to get to improve the result is to increase the FOS 1.5 or higher. This can be better for load and resistance as well as the thermal reliability. So the point number 3 is to add fillets to areas with stress concentration. This will help to contribute the stress and reduce the deformation. It also can increase overall strength at the surface of the design. And the last one is fatigue analysis. Fatigue analysis performed due to repeated thermal and vibration cycles. This will ensure that long-term durability of the design, and it can resistant to failure, so that the bracket can be used at the high speed and high temperature as well as the extreme environment.
In conclusion, mass reduction successfully reduced and this significant lightweighting is primarily attributed to the lower density of magnesium alloy coupled with an optimization geometrical design that efficiently removes non-critical material. However, the presence of material magnesium alloy design achieved a robust FOS of 1.876, and these values falls comfortably within the desired safety range, significantly a much higher margin of safety against material failure, and improve structural integrity despite the mass reduction. Furthermore, the total deformation reduced, indicating that the optimized geometry of the magnesium bracket provides significantly greater stiffness and resistance to deformation compared to the original design, that ensuring better functioning performance and preventing interference with other components. Thank you. That's all for me.